Thank you, Filippo. Thank you, thank you. Okay. Let me see, 21. Okay. Last 2 minutes and then we start, guys. Twenty-three. Okay, guys, so we continue with the lecture of this morning. In particular, this morning, okay, we saw the last topic, I mean, of this morning was represented by polynomial functions. Okay, polynomial functions. So, and in particular, I told you that as a special case of polynomial function, we have, for example, the linear function, which is the function representing the straight line. Then we saw another special case were represented by parabola, or called also quadratic function. Quadratic function. The straight line of order 1 is linear function. The parabola, which is a polynomial function of order 2, is called quadratic function. Then we saw other special polynomial function called powers function, power functions. And we saw 2 different cases, the case in which the integer exponent is even and the case in which the exponent is integer, obviously, and but odd. Now we are going to see a second type of elementary function, which are called rational functions. And here are the general explanation. And as we did before, then we will see simple example, because we want to see the really elementary function, because you must be able to plot them very quickly if you need, for example, at a given step concerning the solution of a particular more general exercise with Professor Dieci. So given 2 polynomial functions, one is this one, f of x. What is it, guys? This is a polynomial function of order n. So, and another polynomial function, bm times xm plus bm minus 1 times xm minus 1, etc., 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 plus b0. So this is a polynomial function of order n, because n is the highest degree of x in f of x. In g of x, instead, the highest degree of x is m. So this is a polynomial function of order m. Now, the function defined as the ratio between f of x and g of x, that is the ratio of 2 polynomial functions, is called rational function. And here I report as a domain. As obvious, guys, if you have troubles, turn on your microphone and stop me, okay? If you have question, problems, stop me, turn the microphone on, and then you can make a question, you can tell me what you want. Okay, so the rational function is f of x over g of x. And which is the domain? The domain, remember, a ratio the denominator of a ratio can never be equal to 0. Okay, so what you need to require, the domain of this function is given by what? By all the x belonging to R such that the denominator is different from 0. So while the polynomial functions are defined on all R, the rational functions are defined for the real values of x, making the denominator different from 0. Yeah, we can skip it. No, skip this note. Yes, you can skip this note. Now we're going to see some very easy example of rational function, which are very really elementary functions that you can plot immediately. Look, for example, at these two cases. These are special cases of a rational function. F of x equal to 1 over x. The numerator is a polynomial function of order 0 because it's the constant. The denominator, x has a degree 1, so because having 1 is like having 1 times x to the power 0, okay? But x to the power 0 is 1. So a polynomial function of order 0 over a polynomial function of order 1. This is another example, a polynomial function of order 0 over a polynomial function of order 2. These are two examples of rational function, very simple function. And we want to plot them to understand how to plot their graph very, very quickly. So we start with the graph of f of x. So f of x equal to 1 over x. Remember, what do you need to require? You need to require that the denominator is different from 0. So the domain is simply x belonging to R with x different from 0. Or if you want to write in a simple way, you can write directly x different from 0. Or if you want to use, you can use a better notation like the one we used this morning in solving inequalities, and also notation we used yesterday, that is as union of, for example, which is another way to write it. Another way to write the domain more formal. No, wait. Okay, another way, but only to review, guys, is x belonging to R, for example, minus the value 0. This is another way to write the domain more formally. Or, for example, only the last one. X belonging to the union of two sets. One set is minus infinite 0, not included, union 0 plus infinite, and then close the outer parenthesis. Okay, these are two other different ways to write the domain. Now, another important things. Guys, do we have pointer? Well, first of all, another thing, sorry. First of all, I want to follow exactly what I did here. Is this function symmetric with respect to the vertical axis? Does it make sense to see if this function is symmetric? Yes. Why? Because the domain is symmetric. In fact, you see, it's made up by the union of this set and this set. You see that this interval and this interval are one the symmetric of the other. So it does make sense. So we compute f of minus x as we did this morning. So this means that you have to put inside x minus x. So you have 1 over minus x, which can be written as minus 1 over x. But minus 1 over x obviously is not 1 over x. So, but 1 over x is f of x. So minus 1 over x is different from f of x. So if you look at the chain of equality, at the end you get that f of minus x is different from f of x. So this function is not even. So it's not symmetric with respect to what? The vertical axis. Is this function symmetric with respect to the origin? We need to check if minus f of minus x is equal to f of x. So compute minus f of minus x. This means, since you have already computed f of minus x, which was this one, this means that you have simply to put a minus in front of this one. So minus 1 over x. Minus and minus gives plus. So 1 over x. So, but 1 over x is exactly f of x. So you can write equal to f of x. So what does this mean? This means that minus f of minus x, look at the chain of equality, is equal to f of x. So this function is odd. Graphically, this means that the graph of this function is symmetric with respect to the origin. Another thing that you can do is the study of the sign of this function. Guys, reason with me. We solved some inequalities this morning and we saw how to study the sign of a function. For example, look at the numerator. The numerator is 1. 1 is always 1. 1 is positive, so the numerator is always positive. Look at the denominator. The denominator is positive when x is greater than 0. Do you agree? Yeah. So for x greater than 0, this ratio is positive. When x is smaller than 0, you have a positive quantity divided one quantity, which is always negative for x smaller than 0. So you have that the function is negative. Therefore, the function is positive for x greater than 0. But what does it mean? X greater than 0 means here, that we are here. For x greater than 0, the ratio 1 over x is positive. So this means that the function lies here in the first quadrant, so you can cancel here below. For x smaller than 0, this ratio is negative. X smaller than 0 means that we are moving ourselves along this line. So 1 over x is negative. So it cannot, the graph cannot lie here. So we can cancel it. Note that this is obvious because our function is symmetric with respect to the origin. And if a function is symmetric with respect to the origin, it means that if you cancel here, you have also to cancel here. If the graph lies in this quadrant, in the first quadrant, then for x smaller than 0, it lies in the third quadrant. Okay, but we still have to understand how to plot this graph. To plot this graph carefully, so I wrote everything here, guys, okay? To plot the graph, I tell you that there are two very important points. Guys, does it make sense to evaluate the function at the point 0? So in other terms, does it make sense to search for a point of intersection with the vertical axis? Which is the equation of the vertical axis? X equal to 0, but by the domain, x must be different from 0. So it does not make any sense to try to search point of intersection with the vertical axis, because therefore, for sure, there is no point of intersection. Well, maybe we can try to find the point of intersection with the horizontal axis. Well, it does not make sense again. Why? Because we have just shown that for x positive, f of x is strictly positive. Strictly positive means that it's strictly greater than 0, so it never crosses the horizontal axis for x greater than 0. Since the function is symmetric with respect to the origin, obviously it doesn't crosses the horizontal axis even for x smaller than 0. But as I want to tell you, there are two very important points, I tell you, and these points are the point 1, 1, because when x is equal to 1, which is the value of your function? You have simply to insert 1 into x. So you have f of 1 is equal to 1 over 1, which is 1. So this function passes through this point. Guys, intuitively, this function is symmetric with respect to the origin. Since it passes through the point 1, 1, for sure it passes also through the point. Here, guys, there is a minus. I know it's very small, but you have a minus. You see, I don't know if you see it. I see it because I wrote it, but it's minus but it's too short. So maybe you don't see it. So minus 1, obviously because it's symmetric. However, if you don't believe me, evaluate your function at minus 1. When x is equal to minus 1, that is you are here, which is the value of y? Put minus 1 inside x, and you get 1 over minus 1, which is equal to minus 1. Okay, so these are two very important points. Now, since the function is symmetric with respect to the origin, guys, it is enough that we study the behavior of the function for x greater than 0. Then, after having plotted the branch of this graph for x greater than 0, we need simply to plot the other by taking the symmetric with respect to the origin. However, guys, I'm telling you that we are doing not a really formal study, but only a study based on the intuitions. So I'm asking you, what has happened as x increases, as x becomes bigger and bigger? For example, when x is equal to 1, f of x is equal to 1. When x is equal to 2, f of 2 is equal to 1 over 2, which is smaller. When x is equal to 3, f of x is equal to 1 over 3, which is smaller. When x is equal to 1 million, f of x is 1 over 1 million. But 1 over 1 million, you understand that is a number close to 0. If x is equal to 1 billion, f of 1 billion is 1 over 1 billion, which is still positive, but a little bit bigger than 0, but only a little bit. So you see that as x increases, you have that the value of this function decreases. So this function tends to become closer and closer to the horizontal axis. We will see maybe one day that this axis, yes, we will see it. Now, so I stop. It's called horizontal asymptote, but I will explain it in another lecture. Because probably we talk about 1 hour and a half one day about limits, even if it's not really the main topic of the course. So, guys, and on the contrary, as you know that this function is defined, well, for all r with the exception of 0. So this function, even if never crosses the vertical axis, gets closer and closer. In particular, what does happen to this function if x becomes closer and closer to 0? For example, which is a number close to 0? Which is a number? For example, consider 1 over 100. You know that 1 over 100 is 0.001, so it's a very small number. So which is the value of the function when x is equal to 1 over 100? You have 1 over 100, which is 100, so it's a huge number. Which is the value of your function when you get even more and more closer to the origin? For example, when x is equal to 1 over 1 billion, which is 0.0000, okay? So it's 1, the value of the function is f of 1 over 1 billion is 1 over 1 billion, which is 1 billion, so it's extremely huge. So as we are getting closer and closer from the right to the origin, we say to 0 plus, because here x is 0 from the right. So we are getting closer, but we never reach 0, but we're getting closer and closer, but never without reaching it. So we say that our function, as x tends to 0 plus, the function becomes bigger and bigger and bigger and bigger. So essentially the function has this pattern, becomes closer and closer and closer as we going closer and closer to 0 to the vertical axis, goes above. Okay. Now, so taking into account, you can plot, and this is a branch. Since the function is symmetric, instead of having to repeat exactly the same consideration, what can you do? You can plot directly the other branch as the symmetric of this one with respect to the origin. Okay? And so this is the graph. So here, for example, the function becomes extremely larger, bigger and bigger. Here becomes more and more negative. Here it tends to 0 from above. Here he tends to 0 from below. But I told you this is about limits concern this behavior. So this is the pattern of 1 over x. As you can imagine, and let me tell you one word if I didn't do it. Yes, let me add that thing now. So pay attention. This function, guys, as I told you, is a special kind of a rational function. And in particular, guys, add it in a note. This is also can be written also, and I do it. So let me write it here. Can be written in another way. Guys, use the property of powers. You can rewrite it as x raised to the power minus 1. So guys, this can be seen also as a power function with negative but integer exponent. So is x to the minus 1. In general, you may have other function of this kind, like f of x equal to 1 over x to the power 3, which can be written, sorry guys, I do not have, as x to the minus 3. So this is also a very simple rational function, and in particular this rational function can also be seen as a power function. But which power function? These are power function with integer negative exponent, and in particular the exponent, the number in the exponent is odd. So if you repeat this analysis with 1 over x to the power 3, x to the 1 over x to the power 5, 1 over x to the power 7, you get again a very similar pattern, that is, all the power function with negative, odd, integer exponents are defined on all R without the 0, so they are not defined on the origin. They are all symmetric with respect to the origin. They pass in particular to the point 1, 1, and so to the point minus 1, minus 1. And as x becomes bigger and bigger, they tend to become closer and closer and closer to the horizontal axis. As x becomes smaller and smaller, that is more and more negative, they tend again to have a graph that tends to approach without reaching it the horizontal axis. For x that tends to become closer and closer to 0 from the right, the value of the function of all these function becomes increasingly bigger and bigger, bigger and bigger. For x that tends to 0 from the left, you have that the function becomes smaller and smaller, assumes more and more negative values. And I repeat, you have a similar pattern, very, very similar, essentially the same pattern for all the power function with negative, odd integer exponent. The only difference, like as I explained before, is the way in which they increase some, depending on the exponent. You have such, we can have a behavior like this. Sorry, I'm doing it. Okay, I did it very poorly, but what I want to say is that all the power functions of this kind that you can write touch each other in the point 1, 1 and in the point minus 1, minus 1. And you have a behavior like this. Guys, I'm not able to do it, guys. It's hard for me. Okay, what I want to tell you, what I want to tell you is that the steepness of the increment as you move in this direction, or the steepness of the reduction if you move in this direction, depends on the exponent. You can use by your own some example, that is, you can study by your own, for example, in one graph, the relationship, the difference between 1 over x and 1 over x to the power 3. And the hint is the following: try to give 1 over 2 to x, and try to give 2x 2 and 3, and you will see which function decreases faster as we move in this direction. Okay, so this allows you to understand which is if this, the one I plotted here, is the graph of 1 over x, and not the one of 1 over x to the power 3, or if this one, the one I plotted originally, is the graph of 1 over x and not the one of x over 3. But I mean, the pattern is the same, only the steepness changing. So you see the consideration is similar to the previous power function, the one with positive integer exponent. Now, similarly, yes? Now, similarly, we are going to plot the graph of f of x equal to 1 over x squared. Again, which is the domain? This is a rational function. You need to require that the denominator is different from 0. to make sense, okay? So domain is x different from 0, or if you want, you can use the other representation of the domain like we did previously. Now, since the domain is symmetric, it makes sense to search for symmetries. So f of minus x means that you have to insert minus x into x. So you have 1 over parentheses minus x, close parentheses, raised to the power 2. But minus x to the power 2 is x squared. So 1 over x squared. But 1 over x squared is exactly f of x. So we have just shown that this chain of equalities holds, so this function is even. That is, the graph of this function is symmetric with respect to the vertical axis. Okay? Now, an observation before going on. Which is the sign of this function? The numerator is always positive. The denominator is always greater or equal than 0, but in particular, we require that x is different from 0. So the denominator, therefore, since it is a square and x, the basis, is always different from 0, is strictly positive. A positive quantity divided another quantity which is strictly positive independently by the value of x gives you a ratio which is strictly positive. So you can cancel everything below the horizontal axis, because for sure the graph of this function will lie completely above the horizontal axis. So the function, as I wrote here, is strictly positive for all x belonging to the domain. As before, guys, for this function, you have two important values. Why are important? They're important because, as I will explain, they belong to all the function like this one, like 1 over x to the power 4, 1 over x to the power 6. And the points are the point 1 of axis 1, when x is equal to 1, which is the value of the function. F of 1 is 1 over 1, which is 1. So the function passes through the point 1, 1. Since this function is symmetric with respect to the vertical axis, when x is equal to minus 1, which is the symmetric of this point, which is the value of f of x? It should be 1. In fact, if you try, compute f of minus 1, that is f when x is equal to minus 1. Put it here. F of minus 1 is 1 over minus 1 to the power 2, which is equal to 1. So it passes through this point. Only intuitively, since the function is symmetric with respect to the vertical axis, to plot this branch, it is enough to study the behavior of the function for x greater than 0, and after having done that, you can plot this branch, and then you can take the symmetric of this branch with respect to the vertical axis, which is this one. In particular, guys, it's very easy. What does if the function passes here? What does happen if x increases? For example, if x is 2, you have 1 over 2 to the power 2 is 4. 1 over 4, which is smaller than 1, obviously. When x is equal to 10, you have 1 over 100, which is very, very small. Okay, so you see that as x increases, the function is still positive, but tends to decrease from above and tends to become closer and closer to the horizontal axis. That is, it tends to 0, the function, as x becomes bigger and bigger without reaching it. Okay, because this ratio is still positive. What does happen instead if we get closer and closer to 0? For example, consider the point 1 over 3, okay, only with an example, 1 over 3, which is f of 1 over 3. Put 1 over 3 inside your function, so you have 1 over, parentheses, 1 over 3 to the power 2. So you have 1 over 3 to the power 2 is 1 over 9. So you have 1 over 1 over 9, which is 9. So you see that 9 is huge. Obviously, if you have 1 over 10, put here 1 over 10. 1 over 10 to the power 2 is 1 over 100. So you have 1 over 100, which is 100. So you understand that if you take a number of x closer and closer and closer and closer to 0, you have always a bigger and even more bigger number. So the function tends to, as we are getting closer to 0, the function becomes closer and closer to the vertical line without crossing it. Since this is the branch, right branch, the left branch, which is the symmetric with respect to the vertical axis, can be plotted immediately by taking, I repeat, the symmetric. Because remember that f of x is equal to f of minus x. So f of 2 is equal to f of minus 2. F of 1 over 100 is equal to f of minus 1 over 100. Okay? And guys, as you can imagine, how can you rewrite it? As x to the minus 2. So this is this rational function is also an example of a power function with negative, even, integer order. In reality, when you say even, with negative even is enough, because if you say even, you establish already that the number is an integer number. Okay, I repeated it, but it's useless, as we did before. So you see, we saw two different kinds of power function. Power function with positive integer exponent, and we distinguish two cases between even and not even. Okay, and we discussed already. Now we saw a special case of rational function, which is represented by another kind, still a kind of power function, but with negative integer exponent. And we distinguish two cases depending on the fact that the exponent is even or odd. In this particular case, guys, what do you think? Which is the graph of 1 over x to the power 4? Can be written as x to the minus 4. Again, you have something like this. I do it poorly. It's something that touch your function here, very similar pattern. Then similar pattern, guys. Only the steepness, as always, when you change the number in the exponent, only the steepness change. Okay, I did it very poorly, but guys, I think you understood. Only the steepness, but when this number or this one is even, you have a similar pattern. Only the steepness changes. Okay, but again, the function that goes, never touches the vertical axis. Before going on, we do other examples, only to play quickly, about the domain, guys. Find the domain of the following functions, because the domain is important. Suppose that you have this function. Which is the domain? Guys, here I use the notation reported previously. I called it f of x and this g of x. I told you, by the definition, that the domain of a rational function is obtained by all the values of x belonging to R such that the denominator is different from 0. Obviously, you don't have to write it. I wrote it only for explanation, to be consistent with the notation I used previously. But you can do it immediately. You have simply to put the denominator different from 0. X belonging to R such that the denominator is different from 0. So put the denominator that is g of x different from 0. So you get x squared minus 1 different from 0, which implies x squared different from 1, which implies x different from plus and minus 1. So you can write this in a very poor way, which is this one, but it's better if you learn also other way to write the domain. So what does it mean, guys? How can you write as a union this domain as a union of interval? Therefore, our function is defined from minus infinity to minus 1, but minus 1 must not be included. So we have these parentheses from minus infinity to minus 1, union, then your function is defined from minus 1 to plus 1, both not included. So union of such type of parentheses. So this means union of this interval without this extreme and this extreme. Then union, our function is defined from 1 to plus infinity. So union 1, which is not included, to plus infinity. As I told you already several times, instead of using these parentheses, you can use the reversed square bracket like I did here, which is the same. Alternatively, there is another way to represent the domain. You can write as x belonging to R minus, when you use this notation, this means that x, the domain is given by all the real numbers with the exception of the set made up by the number minus 1 and 1. So the poorest way to represent the domain is this one. Otherwise, but this is more elegant, and also this is more elegant. But I think They are all four methods are correct. For some professor, however, I know they hate if you write in this way. Okay, but it's still correct. Not very good, not very beautiful to see, but correct. Which is the second function for which we ask it to compute the denominator? This one. Again, what kind of function is this one? A rational function, which is the ratio of a polynomial function of order 2 and the polynomial function of order 1. You have simply to require that the denominator is different from 0. So x minus 2 different from 0, which implies x different from 2. And again, this is the poorest way to write it. You can write as x belonging to what? The function is defined for all r from minus infinity to 2, minus infinity to 2, but 2 is not included, remember, because x different from 2. So you write this one. Union 2, again, not included, to plus infinity. Alternatively, if you want to follow this way, you can write x belongs to R, all the set of the real numbers, minus the set made up by the element 2. The last one. What kind of function is this one? Is a rational function because it's a ratio between a polynomial function of order 1 and a polynomial function of order 3. In particular, this is a power function of order 3. So you need to require that the denominator is different from 0. But when a cube is different from 0, a cube or a power is different from 0 if the basis is different from 0. So we need to require that, you see, x to the power 3 different from 0, which implies x different from 0. And again, I think you understood, guys. X belongs to R minus the set made up by the element 0, or you can write it as a union of interval, the domain, I mean. X belonging to minus infinity to 0, union 0 plus infinity. Observe that 0 is not included. And remember that in minus infinity and plus infinity, you have always to use either this parenthesis or the reversed square bracket. So for the moment, we saw two kinds of function. We saw what? Polynomial function, and among them, three special cases: the straight line, the parabola, so linear function and quadratic functions, and also we saw power function with positive integer exponent. Then we saw a rational function, which are ratio of two polynomial function, and we saw a very specific special case, which was represented again by power function with negative integer exponent. Now we're going to see irrational function. Irrational function, guys, are essentially, you have essentially a polynomial function under a given root. Here I provided some example. Cubic root of x is an irrational function. Square root of x plus 1 over x to the power 3. This is a rational function under a root. Or cubic root of x plus 1 to the power 2. These are examples of irrational function. Irrational, you must have a root, okay? To find the domain of an irrational function, guys, you need to distinguish two cases. Because first of all, look, in part, then I go to the format, I will show, but wait a moment, I wrote everything, so don't be scared. I call Rx, capital Rx, the function inside the root. Well, if the root has even order, like this one, it makes sense among real function if and only if the function inside is greater or equal than 0. Remember, otherwise you have a square root of something which is negative, which does not make sense, or root of order 4 of something which is negative, which make no sense. So in the case in which the index of this root is even, you have to require that the function inside the root must be greater or equal than 0. In fact, I wrote here, guys. Instead, let me finish. If you have a root of odd order, there are no problems. I mean, the function inside, in general, I mean, the root, if you have a root of, let me see, of odd order, the root of odd order itself is defined everywhere, so you don't have problem to have a negative quantity, because the root of a negative quantity makes always sense. an odd root of a negative quantity makes always sense. So, in fact, I told you here, we distinguish two cases. F of x is equal to square root of order 2n times, of the function called capital Rx, where n belongs to n0. What does mean n0? Is the set of the natural numbers without the zero. So essentially, the set of the natural number without zero is made up by 1, 2, 3, 4, 5, 6, 7, blah, 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 blah. Okay, these are the integer, the natural number without the zero. Look, so the meaning. Suppose that n is equal to 1. N is odd, but you see here I wrote 2 times n. So 2 times 1 is 2. So this, when n is equal to 1, we have a square root of order 2. When n is equal to 2, we have a square root of order 4. When n is equal to 3, we have a square root of order 6. So you see that this way works. This is the way to denote the fact that this case corresponds, case A, to the case in which the index of the root is an even number. Case 2, the index of the root has been denoted with 2n plus 1. Obviously, because 2n is always, as we showed just now, is always even. If you add to an even number plus 1, you get an odd number. So case A relates to the domain, as we are going to see, of root with even index. Case B is related to the domain of root function with odd order. In particular, as I just anticipated, if the root, case A is like case A, is the index of the root is even, then the domain of your function is given by all the values of x belonging to R such that this function is greater or equal than 0. Oh, guys, oh, wait. Please, this R has nothing to do with this one. This is the R used as the set of the real number. Here, instead, is the name I used inside, because yes, I don't know, in English it's called radicand, I think. Radicand, the function inside the root. So for this reason I called R of x, but you could have called it G of x, Pippo of x, like you want, S of x. So I called R, but don't confuse, this has nothing to do with this R, okay? This is a function, okay? This is a set of the real number, this is a function. So the domain of f of this function is given by all the real numbers such that the function inside the root of even order is greater or equal than 0. In case B, the index of the root is odd. So in this case, guys, the domain of f is exactly equal to the domain of the function inside the root, because in this case, a root function of odd order imposes no restriction on the domain. So the domain of f in this case is equal to the domain of R. Oh, sorry. Yeah, I repeat, I wrote everything, so guys, you don't need to write. Try to pay attention if you are not. I know that maybe for the majority, I hope this is very too easy. But if someone has problem, try to. I know you are tired. Try to pay attention as best as you can. But I wrote everything, so it's better if you try to pay attention instead. Try to write, because I wrote everything. So among the irrational function, I want to plot really some elementary irrational function, the one you need to be able to plot immediately. For example, one is f of x is equal to square root of x, and the other is f of x equal to cubic root of x. You see, the index of this root is even because it's 2. The index of this root is odd. So we have two different cases. Consider this one. Plot this one first. Which is the domain of this function? Reason with me. You have an even root. You have to require that everything inside the root must be greater or equal than 0. Inside the root you have only x, so you have to require that x is greater or equal than 0. As always, you can represent the domain as you like more. Here I use the simplest method. Okay. Now, question. If I tell you, think your answer to yourself, unless you are so no, proud, how can I say, coraggioso, you are so brave. I'm saying now, I'm going to see if this function is even. I'm going to see that this function is even. Is the professor stupid in this moment, or maybe in all his life, but specifically in this moment, or is the professor smart? So if you are brave, answer, tell stupid to the professor. Okay, no, the professor in this case is stupid. Why? Because the domain, for the first time, is symmetric. No, the domain is not symmetric, because this function is defined only for x greater or equal than 0. So this is not at all symmetric. So since the domain is not symmetric, it does not make sense to search for symmetries. Okay? Furthermore, the domain is x greater or equal than 0. So does it make sense to search the value of f when x is negative? No. So there are several explanations for why it does not make sense. But the first one I want you to outline is that if x, the domain is not symmetric, and in general, when the domain is not symmetric, there are no symmetries. Okay, at least the one we studied together. So the function can, for sure, is neither even nor odd. Which is the sign of the function, guys? Well, a square root is always, in its domain, is always positive. Square root of 9 is 3. Okay, the square root, okay, the square root in its domain is always positive, with an exception, which is the domain x greater or equal than 0. What does happen when x is equal to 0? The square root of 0 is 0. So I wrote here, therefore, that this function is always greater or equal than 0 because it's a square root, a root with even order in its domain, obviously. And so for this reason, you see for x greater or equal than 0. In particular, there are two very important points. One point is the 0. When x is equal to 0, you have f of 0, which is square root of 0, which is equal to 0. So our function passes through the point 0, 0. Then another important point, and I'll tell you later why it's important, is the point 1, because the square root of 1 is 1. So think with me. I told you that the domain is always greater or x greater or equal than 0. This means that the first thing you have to do, you can, since here, guys, the x's are negative and x must be greater or equal than 0, the first thing you can do is this one, immediately, after having done the domain. With this information, you can cancel this part. Now, you studied with me the sign, and I told you that this a root with even index in its domain is always greater or equal than 0. So the domain is x greater or equal than 0. Since the function is always greater or equal than 0, this means that the graph cannot lie below the horizontal axis, so you can cancel also this part. Then you have the point 0, 0. You have this point. To understand why the graph is really this shape, you should need other elements that we still have to study. So I tell you that if you join this point, is not in this way, but the way is this one. And as x increases, for example, square root of 1 is 1, square root of 100 is 10. So it increases, but not so fast. So you have something like this. So this function in particular is concave and has this pattern. Guys, I think you understood the trick. Now pay attention or write, because or add in your note. How can you rewrite square root of x, guys? As x to the power 1 over 2. X to the power 1 over 2. So what kind of function is this one? Have you ever seen a function like this one? Yes, it's a power function. So this special case is an irrational function, and in particular can be seen, it's still an irrational function, and in particular is a power function with positive and rational exponent. Rational because, guys, is a ratio of two numbers. So with positive and rational exponent. And I want you to stress something more. And in particular, the denominator in the exponent, guys, is an even number. So this is I repeat, a rational function, an irrational function, can be written also as a power function. So this is again another power function with, however, which kind of exponent? A rational exponent in which the denominator is even. And all power function of this kind, or irrational function, for example, square root of order 4 of x, root of order 6 of x, which corresponds to x to the power 1 over 4, x to the power 1 over 6, have again a very similar pattern. They are defined in this, I mean, they have a similar pattern. They share in common this point and this point, but someone increases here less faster, and then, okay, guys, I'm not able to, I try with my finger, but I'm not able to see. I mean, what I want to say, you have some pattern like, I mean, you have function like this that, I mean, the same behavior here, very close. I did it too poorly, but I think you understood that you have similar pattern. For example, you go like, let me cancel. I do not write, but I show. For example, if you change the exponent, you have behavior like this. For example, it increase in a similar, very similar fashion, but then it crosses here. Or maybe you have other, depending on this number, can have that increases faster first, then it reduces a little bit, it's increasing, and then stays below the graph. So, so all rational function, irrational function of this kind, or power function of this kind, pass it through this point, and they all have in common 2 points. I repeat, this one, and they have here a point of intersection. So again, the steepness depends. The steepness of the increment depends on this number, which is also the index of the root. Now look at the last one. Not last one, for magari the last one is not the last one. Cubic root of x. Guys, cubic root of x is an irrational function with odd order. An irrational function of odd order has the same domain of the inner function, which is r of x, the inner function. Y equal to x, but y equal to x is a function defined on all r. So also this function, the cubic root, is defined on all r. Does it make sense to search for symmetry? Yes, in this case it makes sense. Why? Since the function is defined on all r, it could be even or it could be odd. Okay, look if it is even. F of minus x is the cubic root of minus x. You can take the minus outside of the root. You have minus cubic root of x, which is obviously not equal to cubic root of x. So chain of equality, and here you have an inequality that tells you that f of minus x is different with respect to f of x. So the function is not even. That is, it's not symmetric with respect to the vertical axis. Then try to see if it is odd. Remember that you have to compute f minus f of minus x, but you computed already f of minus x. So copy it here inside parentheses and put a minus in front of the parentheses. Minus times minus gives plus. What is it? This is exactly f of x. So you see, equal to f of x. So the function is odd, therefore its graph is symmetric with respect to the origin. Another observation I can do, which is the sign of this function, guys. Here you have a root, but the sign of the root depends on of a root of odd order, depends on the sign of x. X is negative, for example, I repeat, minus 27 is the third time I use minus 27. The cubic root of minus 27 is minus 3, so it's negative. So when the radicand is negative, also your function is negative. When the radicand is positive, like for example 27, which is the cubic root, is 3. Also, the root is positive. So when x is positive, or in general greater or equal than 0, I wrote it here, sorry, then the function is greater or equal than 0. When x is smaller than 0, also the root, the cubic root is negative. So that being said, when x is positive, the root is positive. So the first thing you can do is to cancel this part, because you know that the graph will never lie here. When x is negative, as we told you, the cubic root is also negative. So means that the graph lies below and you can cancel everything above. Now, I tell you that there are, again, three very important points. Obviously, one is the origin. When x is equal to 0, which is the root of 0, cubic root of 0, 0. Another important point is 1. In particular, when x is equal to 1, which is f of 1, is cubic root of 1, which is 1. So the point 1, 1. Even without doing this computation, since the function is odd, it is symmetric with respect to the origin, so it will pass also to the point minus 1, minus 1. So this one. Why I tell you that these points are important? Now you should have understood the trick. The trick is the following. So I will not do other study. You can understand that better by after having performed other, ever seen with me or reviewed with me other operation like limit and derivative, that the pattern is this one. But what I want you to realize, why I told you that this point, and this point are important, because as you should be able to image all the irrational function like this one, like for example, cubic root of x, root of order 5 of x, root of order 7 of f of x, share a very similar pattern. The only thing that change is the steepness. For example, you have, as always, you may have something that here increases a little bit faster, then it starts to increase smaller and smaller and smaller, and it crosses here. You can have that it increases here, here, here. It decreases faster and faster. Then at a certain point, it crosses here and it decreases smaller with a lower rate as we move in this direction. Okay, and what kind of function do you think are this one? X to the power 1 over 3. Sorry, 1 over 3. So x to the power 1 over 3. So this kind of irrational function are still what? Are still power function with what? With fractional or rational exponent in which the denominator of the exponent is an odd number. Okay, think about it when if you review this material. Okay, now we introduce another function, which is the so-called absolute value function. So type D of function, absolute value function. Given a function f of x, the absolute value function is written in this way. Y equal to these two vertical lines means absolute value. Okay? In particular, here I provided the definition. Y equal to absolute value of x is equal to f of x whenever the function inside the absolute value is positive. So for all x that makes f of x positive, then the absolute value tells you, oh, I'm happy, I like positive things, so I keep f of x as it is. For values of x that makes f of x negative, the absolute value tells you, I hate to think negative, I like to think positive, so if f of x is negative, if you multiply a negative quantity by minus, minus times minus is plus. So the absolute value function is the absolute value of f of x, therefore is equal to f of x whenever, that is for all the x, such that the inner function is greater or equal than 0, is equal to minus f of x whenever f of x is negative. So what does it mean? That, so in other terms, guys, the absolute value function is always greater or equal than 0. So y, by definition, y is always greater or equal than 0. What does this mean? This means that the graph, if you have an absolute value of a given function, And if you want to plot the graph for sure will lie above always above the horizontal axis. There is a very special case of the absolute value. Typically is introduced, the absolute value function is introduced by using this example, this special case. Guys, y equal to absolute value of x, a special case in which f of x is x. So apply the definition. The absolute value tells you that y is equal to x whenever the function x is positive. When x is positive, guys, or non-negative, when x is greater or equal than 0. So if x is greater or equal than 0, the absolute value like x and says, okay, I don't want to change you, so x. On the contrary, if x is negative, the absolute value doesn't like x and want to change x by multiplying it by minus. So if this is negative, so x is smaller than 0, negative. If x is negative, multiply by minus, what you get? Positive. So this is the representation, for example, of the absolute value function. Try to plot it with me. We want to plot this graph. For example, start from the first branch. For x greater or equal than 0, that is, you are here, you need to plot, which is the graph to plot? Y equal to x. Which is, guys, y equal to x? Y equal to x is the graph of the bisetrix is a straight line. Is a bisetrix, you see I did here, of the first and the third quadrant, first and third quadrant. Intuitively, at the beginning, you can plot it with a non-continuous line. But remember, you have to plot the graph y equal to x only for x greater or equal than 0. So should I color this one? No, because this is the graph of x, but I need to plot the graph of x only for x greater than 0. And only in this part, you see, x is positive. So I color this part. Then for x negative, so here, what do you need to plot? The graph y equal to minus x. Y equal to minus x is this line, which is the bisetrix of the second and fourth quadrant. But for x smaller than 0, I do not have to, obviously, to color everything, because the graph is y equal to minus x for x smaller than 0. So I do not care about this one, and I color this one. As you can see, this is the final graph, the graph of absolute value of x. But as I told you, y is always greater or equal than 0, because you see this graph lies always above the horizontal axis, and only here, when x is equal to 0, absolute value of 0 is 0, and y is equal to 0. But below, you can cancel everything. There is also another way to plot this graph. Can I cancel for a moment? Ah no, voglio cancellare le ultime cose che ho fatto. No. Fate cancellare. Okay, guys. Alternatively, you have a way to proceed. Plot this one. Okay. This is the graph of x, y equal to x. But for x smaller than 0, we need to plot what? The graph of minus x. So the graph of minus x, what does it mean? Suppose that here the value of the function, sorry, I really did it poorly. Suppose, guys, I'm trying to touch, I want to do this point on the line. Suppose here you have 1. So in the axis, here, minus, you have 1, and 1, sì, stupido, so minus 1. Here you have also minus 1. So this is, I repeat, the graph of y equal to x, which is the graph of y equal to minus x. X is minus 1. The graph of minus x, when x is equal to minus 1, will be minus 1. That is, will be this point. What I'm saying, guys, what I want to tell you, and when the function here assumes value minus 2, for example, when you have minus 2, okay, have troubles, guys, then you go below until you touch here, and then you find here the point. And if you go horizontally here, you have -2, okay? -2. So the value is -2, but the opposite, but you need to plot this graph. The graph of minus y equal to minus x, that is -2, which is 2. In other terms, what I'm saying is that you can simply plot first this one, the graph of y equal to x. Then, for x smaller than 0, you have to take the symmetric of this branch with respect to the horizontal axis. How can you do it? Simply by multiplying by -1 all the values you can read here of your function. So essentially take the symmetric and cancel everything below. Cancel everything. And again, this is another way to plot this graph. Here we're going to see, let me see. We arrive here, then we do the break, okay? We do then, I think 5, 6, 7 minutes, okay? And then we do the break. Examples. Plot the graph of the following functions. Y equal to absolute value of x squared, y equal to absolute value of x to the power 3, y equal to absolute value of cubic root of x. So this is also a way to review again this special power function we saw. Guys, in principle, one should distinguish two cases, but make a reason with me. Look, absolute value of x squared. But remember, the absolute value of x squared is equal to x squared, reason with me, when what? When x squared is greater or equal than 0. Is equal to minus x squared when x squared is negative. Guys, but can x squared be negative? No, x squared is always greater or equal than 0. Since the quantity inside the absolute value is greater or equal than 0 always, the absolute value is happy because he has to do nothing. So copy it x squared, which is the graph of x squared, guys. Y equal to x squared is a parabola. So you can plot it immediately because it's a parabola. In particular, is this parabola convex or concave? Which is the coefficient of x squared? Is 1, which is positive. So the parabola is convex. Which are the point of intersection of the parabola with the horizontal axis? Does it make sense to search them? Well, yes. Which is the equation of the horizontal axis, guys? Y equal to 0. So this means put x squared equal to y, therefore to 0. And what you get? X squared equal to 0 implies x equal to 0. So we find out one point of intersection. And you know, when you have only one point of intersection with the horizontal axis, this means that the point of intersection is obviously the vertex. So you have to do nothing more. You simply to plot directly this parabola. And the graph of this parabola is equal to the graph of the absolute value of x squared. Absolute value of x to the power 3. Now, apply the definition of absolute value. The absolute value gives us x to the power 3 whenever x to the power 3 is positive or equal to 0. Guys, x to the power 3 is positive when? Is positive when the basis x is positive. When x to the power 3 is 0. Is 0 if the basis is 0. So, for x greater or equal than 0, x to the power 3 is positive or and also greater or equal to 0. Therefore, the absolute value tells you, okay, I copy you as you are, x to the power 3. However, when x to the power 3 is negative if the basis is strictly negative. That is, if x is smaller than 0. So when x is smaller than 0, x to the power 3 is negative. But the absolute value doesn't like the fact that x to the power 3 is negative. So it goes away, but multiplying x to the power 3 by minus. So minus x to the power 3 if x is smaller than 0. So now we have all the elements to plot the graph of the absolute value. I will not repeat it, but I will not explain it again, but we plotted already the case y equal to x to the power 3, because what was it? This was the graph of a power function of order 3, and the graph was this one. Look, was symmetric around the origin, it passes to the point 1, 1, and here, okay, this is the graph of x to the power 3. But remember, we need to plot the graph of x to the power 3 if x is greater or equal than 0. So here we need to plot the graph of x to the power 3, which is this branch. So we do not color this one. Now, for x smaller than 0, here, you see here, x is smaller than 0, we need to plot minus x to the power 3. But guys, what I told you before, you don't have really to do nothing now, because to get the branch minus x to the power 3, it is enough to take the symmetric with respect to the horizontal axis of this branch, which was the x to the power 3. So take the symmetric with respect to this branch, and you get this one. What you get is this function. Okay, as you can observe, as always, the graph of the absolute value lies always above the horizontal axis, or on, because you have here this point 0, 0. But you see, everything below has been cancelled. Now the last, I think, and then we do the break. Plot the graph of y equal to absolute value of cubic root of x. We plotted already the graph of cubic root of x. In particular, if you remember, the graph of cubic root of x is this one. Look what I touch, look what I touch. Go below, and you have this one. It was symmetric with respect to the origin. We did it previously. I'm asking you, no, I'm asking myself. No, I don't. I ask nothing to. I simply continue. I don't ask. Okay, stop. I don't know what I have to say. So absolute value of cubic root of x. So the absolute value gives you cubic root of x whenever cubic root of x is positive. We have already seen that cubic root of x is positive if the radicand is positive, and is 0 if the radicand is 0. So this term is greater or equal than 0 whenever x is greater or equal than 0. So for x greater or equal than 0, the absolute value tells you that you need to plot this graph. On the contrary, when x is negative, also the cubic root is negative. So this cubic root is negative, the absolute value make it positive by multiplying it by minus 1. So minus. So we need to plot this graph, but apply the previous trick. First plot this graph with a non-continuous line, the graph of cubic root of x, because we derived it previously. Then if x is greater or equal than 0, then you have to color it with a continuous line for x greater or equal than 0. For x smaller than 0, look, you don't have to plot the graph of cubic root of x, but you have to plot the graph of the opposite, minus cubic root of x. But the opposite means that if the value here is minus 2 of cubic root of x, the value of minus cubic root of x is 2. If here the value is minus 6 of cubic root of x, the value of minus cubic root of x is minus 6 is 6. So in other terms, you have to take the symmetric of this branch with respect to the horizontal axis, and you get this one. If you want to play at home, and then we stop, oh no, accidente, un altro che mi state mandando gli incidenti in silenzio. Okay, if you want to verify that this function and this function, these and these are even to plot, to play. The last things, and really we stop and we do the break. Observation: square root of x squared is equal to x? No, it's not equal to x. Square root of x squared is equal to plus minus x? No, because the square root of something must be always positive. In particular, to be precise, the square root, the square root function must be always positive. So the square root of x squared is equal to absolute value of x. So you have this very important identity of mathematics that tell you that square root of x squared is not this one, is not equal to plus minus x, but is equal to absolute value of x. That is, square root of x squared is equal to x if x is greater or equal than 0. Is equal to minus x if x is negative, because the square root is always positive or greater or equal than 0. In this way, you see that when x is negative, take minus x, which make it positive. So the graph of square root of x squared is equal to the graph of x. Now, okay, guys, you can rest 16 minutes of break. We start again at half past 3 p.m. Okay?
Okay, thank you.
Thank you, guys. You can go to rest, guys. You can go. I turn on my microphone. Unless you have something to ask, you can ask me, okay? If you ask me nothing, I go also a little bit away to drink something, to drink water. But if you have something to ask, you can ask me, okay? I'm still here. Okay, since no question, I go to drink something, water. Okay, guys, 1 minute and we start. Oh, yeah. So, guys, now, we need to start now. Now, 1 minute because it's already 3 p.m. and a half, 3:30 p.m. So, guys, we need to continue, and in particular, guys, if you go back to the previous, to the PDF we were considering, we just finished to talk about the absolute value, and now I need to introduce exponential function and logarithmic function. However, to reach this task, since I know that several students have problems, especially for exponential powers and logarithms, first, before introducing exponential function and logarithmic function, we are going to see back power. We're going to review properties of powers and the definition of logarithms and properties of logarithm, and we will make a couple of exercises to make only practice. So you see, insert file power and logarithm. So if you go in the folder I uploaded, you have a file powers and logarithm. Let me, I already opened it. Yes, power and logarithm. Let me, power and logarithm. You see, power and logarithm. Let me increase the dimension. And okay, powers with real exponent. The power a to the power beta is defined for every value of a, which is the basis, positive, and for every beta belonging to R. So a must be strictly positive, the basis, and beta, the exponent, can be any real number. And now we are going to see the property of the powers with the real exponent defined in this way. Suppose you have a product a to the power alpha times a to the power beta. You have the product of two powers with the same basis. The result is the power with the same basis, and exponent the sum of the exponents. So a to the power alpha plus beta. If you have a fraction a to the power alpha divided a to the power beta, you can obviously rewrite in this way. And for example, this is not a q, okay, it's an a written in this way. You can write it, for example, as a product. You can write it as a to the power alpha times 1 over a is still a, okay, it's written not very well, but it's a to the power beta. Now, you can rewrite 1 over a to the power beta by using a property we have already used before of the exponents. That is, you can put a in the numerator, sorry, and you change sign of the exponent. So you get a to the power alpha times a to the power minus beta. This is again a product of two powers with the same basis, and the result by using the first property is a power with the same basis a, and as exponent the sum of the exponents, so alpha plus minus beta, therefore alpha minus beta. Okay, in other terms, we have just shown that if you have the ratio of two powers with the same basis, instead of performing all the steps I did, you can have as a result a power with the common basis, which is a raised to the power alpha minus the exponent of the denominator, okay, a to the power alpha minus beta. So remember, a typical mistake we still see also in the master is the following: a times to the power alpha times a to the power beta is a to the power alpha times beta plus beta. Don't do a to the power alpha times beta. It's completely wrong. You can do alpha times beta in this case if you have a so-called power, because this is a power of power. You have a to the power alpha, everything raised to the power beta. This is called power of a power, or power, sorry, power of a power. And the result is a, the basis, raised to the product of the power. So only when you have power of power, you can do the product of the exponent. But when you have a power times another power with the same basis, you have to do the sum of the exponents. So here the result, when you have a power of power, is a to the power alpha times beta. For example, look here, I read first this one. Suppose instead, I prefer to read from this part. Suppose you have the product, oh, they're making noise. Maybe they are go further from here, I don't know. So suppose you have a product, guys, between a to the power alpha and b to the power alpha. What kind of product is this one? Is a product between two powers with different bases but with the same exponent. When you have a product between two powers with different bases, a and b, but the same exponent, alpha, the result is simply the product of the bases, a times b, raised to the common exponent. I prefer to read also this part from here. Suppose you have also a ratio between a to the power alpha and b to the power alpha. It's still alpha, okay? So you have a ratio of two powers with the same basis, with different bases and with the same exponent. When you are in a situation like this, you can do the ratio of the bases raised to the common exponent. So a over beta raised to the power alpha, where alpha also belongs to R. Alpha and beta belongs to R. A must be, so A and B must be strictly positive. Alpha and beta are real numbers. So these are properties of the powers. Okay. So if you now by reviewing this property, you should remember, you should be, I mean, do what you want. Sorry. Logarithms, which is an enemy for several students, but logarithm has nothing terrible, nothing special. It's a simple operation. So the logarithm, we read the definition together, with basis a, where a must be strictly positive and different from 1, of a positive number b. So the logarithm with basis a, where a must be positive and different from 1, of a positive number b, is the number c, which is a real number, such that a to the power c is equal to b. So I repeat, the logarithm with basis a of b, where a is positive and different from 1, and b is strictly positive, is the exponent c you have to give to the basis a to get b. So the logarithm with basis a of b is the exponent c you have to give to the basis to get b. So this is the definition of the logarithm. C, remember, is this one, belongs to R. So in other words, it is the real exponent c to give to the basis a to get the number b. Formally, the logarithm with basis a of b is written in this way. C, which is the logarithm with basis a of b, so c, which is the logarithm with basis a of b, is the exponent c you have to give to the basis a to get c. So if you write this, I mean, this expression and this expression are perfectly equivalent. For this reason, I wrote a raised to the power c equal to b if and only if c is the logarithm with basis a of b. So I repeat for the last time. C, which is the logarithm with basis a of b, is the exponent you have to give to the basis a, that is this one, to get b. From this one, it follows the property that I will describe in a moment, but yes, this is exactly what I just told you. I repeated it. So this is a very, very fundamental relationship, which is the definition of logarithm, and this clarifies what a logarithm is. C, I repeat, is a logarithm. A is called the basis. B is called the argument of the logarithm. So don't write because I repeated everything many times. So we are going to see the properties of logarithms now. Some property of logarithm. Suppose that B1 and B2 are two positive numbers, two strictly positive numbers. Remember that the argument of the logarithm B must be strictly positive. So the logarithm with basis A of what? The argument in this case is the product between B1 and B2. So the logarithm of the product, guys, is equal to the sum of the logarithm. Therefore, the sum of the logarithm of A with basis A of B1 plus the logarithm with basis A of B2. Guys, as I told you, we have to require that B1 and B2 are both greater than 0 in order to have this property. Because, guys, suppose that B1 is minus 1 and B2 is minus 2. Minus 2 times minus 1 gives minus 1 times minus 2 gives you 2. Logarithm with basis A of 2 makes sense. But since B1 is minus 1 and B2 is minus 2, the property does not hold. So the property holds if B1 and B2 are both positive. Okay, so it's not enough that the product is positive because if the factor are negative, this does not make sense and this does not make sense, because if you go back to the definition, the logarithm of a number B, where B must be strictly positive, if the exponent C, you have to give to the basis A. But think with me for a moment. The basis A is positive. Give a real number to the basis A. The result you get must be always strictly positive. For this reason, B must be strictly positive. So the logarithm of a product is the sum of the logarithm, okay, under this hypothesis, okay? B1 and B2 are both positive. Look at the logarithm with basis A of B1 over B2, where both B1 and B2 are strictly positive. The logarithm with basis A of a ratio is the difference of the logarithm, in particular, the logarithm of the numerator, I mean, logarithm with basis A of B1 minus logarithm with basis A of B2. Let me close the window. And also this door. Okay. You see, so these are very important property. Now, third property, if B is positive, then logarithm with basis B, with basis A of B to the power K, these guys means that only B is raised to the power K, okay? Only B is raised to the power K, okay? Not all the logarithms. So if you, no, it's correct in this way, but if you have trouble to understand, I put a parenthesis here. So the logarithm with basis A of B to the power K can be written as K. So the exponent of the argument can be written as a multiplicative term in front of logarithm with basis A of B. Okay, so this is the third property. Also, this property is very important. Logarithm with basis A of A is equal to 1. Why? Guys, 1, which is 1, guys? By definition, 1 is this one, is the logarithm with basis A of A. So call it C for a moment. Call it C. By definition, the logarithm, call it C for a moment, is the exponent you have to give to the basis A to get the argument, which is the exponent you have to give to the basis A, this one, to get this number. Obviously, C must be equal to 1. So in general, logarithm with basis A of A is equal to 1. Logarithm with basis 3 of 3 is 1. Logarithm with basis 2 of 2 is 1. And here this is the explanation, because you have to apply, I apply just the definition of logarithm. The logarithm of a number A is the exponent you have to give to the basis A to get A, which is this exponent. Obviously 1. To have an equality, you have to put here 1. So this is true. Which is the logarithm with basis A of 1? Again, reason with me. Which call C the logarithm. The logarithm is the exponent, call it C, you have to give to the basis A to get the number 1. A is strictly positive. How can you get 1? You know that every number raised to the power 0 gives you 1. So C, which is the logarithm, is 0. So logarithm, independently by the basis of 1, is always equal to 0. Okay, guys. So let me see. First, previously I had something in my mind. Let me see if I told it. And guys, from this definition, go back. I told you that by definition, this is definition, the logarithm is the real number C. You have to give to the basis A to get B, and can be denoted in this way by definition. So A is equal to what? A to the power C, but C is the logarithm with basis A of B. So I simply substituted into C its definition. So we have A to the power logarithm with basis A of B, and this is equal to what? B. So if you have raise A to the power logarithm with basis A of Gigi, the result is Gigi. If you raise A to the power logarithm with basis A of 7, you get 7. So if you want, you can add also this property. This property is less important, guys. I reported it, but you can forget about it, I think. But maybe I read it with you. The other property is very important. This is less useful. So if you have the logarithm with basis C of B, this can be written as logarithm with basis A of B, so a logarithm with another basis different from C, call it A, of B, times the logarithm with basis C of who? Of A. So this rule is called the change of basis rule, but well, for the moment skip it unless I did something important below to apply. But well, the other properties are very important. This one, okay, is not so useful. I don't think you need it on the course of mathematical method and tools. So if you forget it, it's not so problematic. Here I did some easy exercise to make practice with logarithm with the property. Let me see. To review, we are going to study very simple exercise. To do a very simple exercises. Compute the following logarithms. Okay, see without using the calculator. So if we can, logarithm with basis 10 of 1000. Guys, are you able to write 1000 as a power of 10? Because 1000 can be written as 10 times 10 times 10. So 10 to the power 3. So I simply substitute, I wrote it as a power. Now, if you use property C, I told you that the exponent of the argument can be written as a multiplicative term in front of the logarithm. So you have 3 times logarithm with basis 10 of 10. But remember, property D, logarithm with basis A of A is equal to 1. So we apply just now C and now D. Now, logarithm with basis 10 of 10 is 1. So 3 times 1 is 3. Okay. Now try to, again, compute also the following logarithm, if it is possible, guys. Logarithm with basis 1 over 2 of 4. Okay. 4, guys, can be written as a power. For example, the simplest I have in my mind is 2 to the power 2. Okay, so since I wrote this logarithm in this way, the argument as a power, you know that the exponent of the argument can be written in front of the logarithm falls down, okay, in front of the logarithm. 2 times logarithm with basis 1 over 2 of 2. Guys, are you able to rewrite 2 as a power with the basis 1 over 2? Well, 1 over 2 to the minus 1, guys. How can you write 1 over 2 to the minus 1? I write it here. 1 over 2 to the minus 1 means 1 over 2, which can be transformed into the product between 1 and 2. So 1 times 2 over 1. Okay, if you want, I write here 1 times 2 over 1, which is 2. So another way to write 2 is by writing 1 over 2 to the minus 1. I did it because I know that this basis is 1 over 2. And then see, minus 1 is the exponent of who? Of the argument. So put it here. Minus times 2 is minus 2. Then you have logarithm of 1 over 2 with basis 1 over 2 of 1 over 2. But again, logarithm with basis a of a is 1. So you have minus 2 times 1. Okay, I did here, guys, the operation. Okay, here I explain better, maybe. Okay, so again, we applied which property? C and D. Now, C equal to logarithm with basis 5 of 125. Are you able to express it as a power? Especially, it's good if you're able to do it directly in one step. Here, guys, you could have done it in one step, but for me, it was easier to write it by doing this step. But one can have done it in one step only by writing 1 over 2 to the minus 2. But okay. Look here. Are you able to write 125 as a power with basis 5? Well, 5 times 5 is 25. Times 5 is 125. So you can write it as 5 to the power 3. Again, the exponent of the argument can be written as a multiplicative term in front of the logarithm. So 3 times logarithm with basis 5 of 5. But again, property, logarithm with basis a of a is equal to 1. 3 times 1 is equal to 1. Let me open again the window because it's too. I cannot breathe. I cannot breathe. Sorry. So I open the window again. Let me open the other door. I'm back, guys. So find, guys, the argument of the following logarithm. So we have the argument is b. We have logarithm with basis 10 of b equal to 4. Apply the definition. Remember, 4 is c. Remember, is the logarithm because this is the logarithm is equal to 4. So 4 is the logarithm. So 4 is c is the exponent you have to give to the basis a to get b. So b is equal, if you see, a to the power c. So b is equal to a to the power c to the power 4. Okay, you can stop here, 10,000. Okay. Again, this exercise isn't, even if they are stupid for you, okay, if you are already good, okay, you don't care at all, really, they are stupid. But if you never studied logarithm, these are useful because you apply the definition again and again, the property again and again, so you make practice to learn them. So again, which is the definition of a logarithm? The logarithm is this number, because this logarithm is equal to 3, so this is the logarithm. The logarithm is the exponent c. You have to give to the basis square a, which is square root of 3, to get b. So b is equal to square root of 3a to the power 3. Okay? Okay, here one can write directly square root of 3 times square root of 3 times square root of 3 is 3 square root of 3. Alternatively, to play also with the properties of powers, which is square root of 3. Square root of 3 can be written as 3 to the power 1 over 2. And everything raised to the power 3. So what is it? A power on power. And the result is a power with the same basis, 3, and the power, the product between 1 over 2 and 3, the product of the exponent. So 3 to the power 3 over 2. So play again. How can you rewrite it as a root? Remember, I add a step. The index here, the 2 here, is the index of the root. The index here instead is the power of the basis under the root. 3, so is square root of 3 to the power 3. I'm simply adding a step, guys. So it's not 33, but it's 3 to the power 3. Then how can you establish that then the result is 3 square root of 3? So here you have the root is index 2. So you have to do 3 divided by 2, which is the index of this exponent, divided by 2 gives you 3 divided by 2 gives you 1 with remainder 1. So this means the result is 1. So this means that you can take 3 outside to the power 1. Square root of what? 3 to the power, I told you the remainder of 3 divided by 2 is 1 also. So inside you have 3 to the power 1. So 3 square root of 3, property of high school. Okay. Only to talk. Logarithm with basis 1 over 25 of b equal to minus 1 over 2. So this is the logarithm. The logarithm is equal to minus 1 over 2. By definition, the logarithm is the number c, so minus 1 over 2. You have to give to the basis a, which is 1 over 25, to get b. So b is equal to the basis raised to c, which is this number. Okay. If you change, guys, the sign of the exponent, you have to take the reciprocal of this number. So I changed the sign of the exponent, but I took also the reciprocal of this number, which is 25. Now, this means square root of 25, which is 5. Ok? Ma cosa ho già saltato avanti? No, fate vedere. Ah, mi sa che ho saltato una pagina. Ok, ma non era importante. I avoided... let me see. Okay. Now, guys, skip for the moment. Yes, we do exercise 4 for last. Yes, when I scanned, I forgot because, okay, I noticed it last year, but I forgot. When I scanned, this was the page 9.3. Oh. Then there was page 9.4, which is, unfortunately, when I scanned, I inverted the order. So here it was page, mi sono dimenticato, 9.4. Okay, so we did already this exercise. We avoid for the moment exercise 4, and we continue with page 9.4. So I go to the last page. So again, we make other confusion. I mean, other exercise back. Here we want to compute the expression, I mean, the values of this logarithm, at least if we can. So c equal to logarithm with basis 9 of 27. Are you able to write, well, we cannot write it as a power of 9, but 27 can be written as 3 to the power 3 because, okay, 27, you know that I did this example, 3 to the power 3 times 3 times 3, 27. So 3 to the power 3. The exponent of the argument, I mean, is 3. So you can copy the exponent in front of the logarithm as a multiplicative term, and you get logarithm with basis 9 of 3. Guys, can you rewrite 3 as a power with basis 9? Well, I applied this trick. Everything has been cut in the scanning procedure. I mean, a little bit. So, well, I realized that 3 can be seen as the square root of 9. Do you agree? The square root of 9 is 3. So I wrote square root of 9. Then, guys, here is not a typo, but a scanning procedure. You see that this part has been cut. How can you rewrite square root of 9 by using power? As 9 to the power 1 over 2. So please check. It's not a mistake, but this has been cut, you see, by the scanning procedure. So it's not to the power 2, because if you don't do the operation, unless you are good enough and you remember that and you understand immediately that there is a that everything has been cut, you can say, why? He wrote square root of 9 and then 9 to the power 2. Instead, here is 9 to the power 1 over 2. Then 1 over 2, put 1 over 2 in front of the logarithm. So 3 times 1 over 2 is 3 over 2. Logarithm with basis 9 of 9 is again 1. So the result is 3 over 2. We do the last one of this type. Compute this logarithm. Again, are you able to write 49 as a power with basis 1 over 7? Maybe, but it's better for me to do step by step. It is easier for me to write 49 as a basis with power 7 first. Okay, one can do it immediately if he's able, okay, but I prefer, since I am tired, even if I am the professor, I'm tired, so I prefer to do step by step, okay? So 7 to the power 2, okay? Then 2 is an exponent of the argument, so you can copy it in front of the logarithm. So 2 times logarithm with basis 1 over 7 of 7. Now, I don't know, I know that is easy, but to me it's easier if you do this additional step. How can you write 7 as a power with basis 1 over 7? We did it before when we wrote 2 as 1 over 2 to the minus 1. So you can write 7 as 1 over 7 to the minus 1. Oh, they are back. Oh. No, fanno presto, they will do it easily. So now minus 1 is the exponent of the argument, put it in front of the logarithm, so minus 1 times 2 is minus 2. Then logarithm with basis 1 over 7 of 1 over 7, which is 1, minus 2 times 1 is minus 2. Okay. Another couple, some other exercises. Compute the value C of the following logarithms and verify that your solutions are correct. So we have not only to compute the logarithm, but we need to verify that our solutions are correct. Before we computed only the value C of the logarithm, but without doing a proof. Now we do the proof. So C equal to logarithm with basis 8 of 2. Well, are you able to write 2 as a power of 8? Well, first of all, I know that 2 can be seen as the cubic root of 8. Okay, 2 times 2 times 2 gives you 8. So the cubic root of 8. Now, cubic root, a root can be written equivalent by using the power. So as 8 to the power 1 over 3. Again, 1 over 3 is a multiplicative constant, put it here, logarithm with basis 8 of 8 is 1, so 1 over 3. So this is the result. Is the result correct? Well, taking into account that saying that C is the logarithm with basis A of B, that is, as we wrote here, is equivalent to say that C is the exponent we have to give to the basis A to get B, we verify. So A raised to the power C, A is 8, okay? A is 8, you see? C is the number we got to the power 1 over 3, which is square root of 8. Sorry, guys, please, cubic. I did correctly, but I forgot the cubic. Cubic root of 8, which is equal to 2, which is exactly B. So this is the proof that the result we got is correct, because we applied the definition, we took into account that this is equivalent to this one. So we substituted in A the basis, we substituted in C the result we got previously, and we saw that A raised to the power C effectively gives us 2, where 2 is exactly B. So we should be happy that the result works. Now, C logarithm with basis 1 over 2 of root of order 5 of 16. First, I want to delete the root. To delete the root, I transform the root into a power. So you can write it as 16 raised to the power 1 over 5. Again, 1 over 5 can be written in front of the logarithm as a multiplicative constant because it is the exponent of the argument. Now, one's really smart can do everything in one step. Since I'm not smart, I do it in several steps. Guys, can you rewrite 16 as a power? Yes, for example, as a power with basis 2. 2 times 2 is 4, times 2 is 8, times 2 is 16. So you can write 16 as 2 to the power 4. Then again, copy the 4 in front of the logarithm. So you have 4 over 5 times logarithm with basis 1 over 2 of 2. Now it's easier again. Are you able to write 2 as a power with basis 1 over 2? Yes, we did it already 2 times. So you have simply to substitute to 2, 1 over 2 to the power minus 1. Okay, if you go below, in fact, you see 1 over 2 to the power minus 1. Copy the minus here. And then you have logarithm minus 4 over 5 times this one, which is obviously equal to 1. Minus 4 over 5 times 1 is minus 4 over 5. Now we make the check. To make the check, we need to show that a raised to the power c is equal to b, where b is the root of order 5 of 16. Okay, so a to the power c. A is 1 over 2. C is the result we have just obtained, so 4 over 5. Okay, I could have done it directly. Oh, skip this step. Skip this step, please. Otherwise, I did. No, it's correct. But no, don't cancel. Skip this step, but they are correct, obviously. So how can you rewrite this? Suppose you want to change the sign of the exponent here. If you change the sign of the exponent, you have to take the reciprocal of the basis, which is the reciprocal of 1 over 2. It's 2. So 2 to the power 4 over 5. So what I'm saying is that this step were correct, but I don't know why I did so long. Look, so long steps. So you can do in a moment this one. Then there is a trick. What we need to prove? We want to prove that a to the power c, that the result of this operation is root of order 5 of 16. I want really to get the number expressed in this way. Guys, this is the exponent. Are you able to see the exponent at the product of two numbers? In particular, one with index 1 over 1 with the value 1 over 5. Well, you can look at 4 over 5 like as to the product between 4 and 1 over 5. Okay, so so if you want, you can add a step. You can write 2 raised to the power 4 times 1 over 5. Okay, 4 times 1 over 5. But remember that the power of power is a power with the same basis and as exponent the product of the exponent. So in other terms, I can see this number as the result of a power of power, in particular of 2 to the power 4, everything raised to the power 1 over 5. I am applying the property of the power in the opposite direction, because typically you start from this operation, then in order to compute it, you do this times this and you write this one. Instead, since I want really to get the result written in this way, I did the reverse operation. From this, I decomposed this power as a power of powers. So to reach this task, first I perform this step, which is perfectly true. Okay, then 2 to the power 4 must be raised to the power 1 over 5 to get an equivalent expression. But to say 1 over 5, it means that 2 over 4 is the radicand, and you have to put the radicand inside a square root of order 5. Sorry, a root of order 5, not square root, a root of order 5. 2 to the power 4 is 16, so you see that the previous result, minus 4 over 5, was effectively correct, because now we did the step and we got exactly the argument of the logarithm. So our computation was correct. Oh, no, I don't like that. We do this one, okay? Guys, we do this one now. So C is equal, compute this logarithm, is logarithm with basis square root of 2 of root of order 5 of root of order 8. Okay, one can here perform several steps, guys. Here I perform some steps. So first of all, I wrote it as logarithm with basis square root over 2 of what? Of the radicand, which is square root of 8 raised to the power 1 over 5. Okay, one can do it in one step, but I prefer to repeat the step more times. So 1 over 5 can be written in front of the logarithm, since it is the exponent of the argument only, okay, remember? Now, square root of 8. Guys, square root of 8, which is square root of 8? Is like square root of 2 to the power 3. You remember, square root of 8 is square root of 2 to the power 3. So again, how can you write it? You can take 2 outside, and you have to raise it to the power 1, and inside you still have 2 to the power 1. So 2 to the power 2 times square root of 2. Okay, so I simply square root of 8 can be written in this way. Okay. Now here, let me see what I did. I performed 2 different approaches. Okay, 2 different approaches to solve it. So look at the first one I followed. What is, oh sorry guys, ma ogni tanto parte. Guys, can you see something? I want to apply a property we saw, but that we still haven't applied today. Guys, you can see that 2 square root of 2 can be written as the product between 2 and square root of 2. But if you go back, the logarithm of a product, dove l'ho scritto? Where I wrote it, is the property I want to apply is this one, because we have something like logarithm with basis square root of 2 of 2 is b1 times square root of 2, which is b2. So it's the logarithm with basis square root of 2 of b1, which is 2, plus logarithm with basis square root of 2 of b2, which is square root of 2. So go below with me and we will see. We apply this property now. Dove siamo? Mi sono perso. Qua sotto. We are here. Sorry guys, I was talking in Italian. So 1 over 5, now apply the property, so open a parenthesis because now we want to split this logarithm into the sum of 2 logarithms with the same basis, square root of 2. So logarithm with basis square root of 2, logarithm with basis square root of 2. Of what? Of b1, which is 2, and the other of b2, which is square root of 2. But first of all, which is the logarithm with basis square root of 2 of square root of 2 is 1. So you see that I added plus 1. Furthermore, I did already a step here. Are you able to write 2 as a power of the basis? Well, 2 can be seen as square root of 2 raised to the power 2. Okay, because square root of 2 times square root of 2 gives you 2. Okay, so I wrote it in this way. Then do this step with me. 2 can be written in front of this logarithm, and then you would have 2 times logarithm with basis square root of 2 of square root of 2, which is 1. So 2, these 2 times 1 is 1 plus the other 1. So you see, this is the reason why I wrote here 2 plus 1. 2 plus 1, 3, 3 over 5. Then let me see what I did. An alternative way, for example, is the one I wrote here. Maybe you find other, guys. You can find other ways, but in all the ways you have to apply properties of logarithms or exponential. For example, let me see what I did below. I copied this one, and look, I wrote 2 square root of 2 as the product of 2 powers with the same basis. In fact, this can be written as 2 times to the power 1 times square root of 2 can be written as 2 to the power 1 over 2. Okay, then transform it into, do the product. You have a product of 2 powers with the same basis. The result is the power with the same basis 2, and as exponent, the sum of the exponent. You see, we are applying again the property of powers we studied at the beginning of this presentation of 4 pages. So you have 1 plus 1 over 2, which is 3 over 2. Then again, no, in this case, I want to save something. Guys, Okay, I did the step, so I tell you the step because I wanted to say I put here only the 3 because I want to press. Okay, stop. I read and I do first. Logarithm. Okay, you see I copied everything. Then you have 2 to the power. Again, 3 over 2 can be seen as a product between 1 over 2 and 3. So I can write this power as a power of power, like 2 to the power 1 over 2 to the power 3. Because if you apply the property of powers, you have 2 times 1 over 2 times 3, which is 2 to the power 3 over 2, which is the same. So I'm simply applying again the property of powers. Then take the 3, put it here. 2 to the power 1 over 2 can be written as square root of 2. Let me see if I did it. Yeah, 3, put 3 here. Here I repeat, these can be written as, guys, 2 to the power 1 over 2 is square root of 2, okay? So logarithm with basis square root of 2 or square root of 2 is 1. So 3 times 1 over 5 is 3 over 5. No, I don't want to do the check. No. Oh, no. I don't want to do the check. Okay, do the check. And then we finish this exercise. To check that the result is correct, we have to remember that this is the logarithm. That is the exponent, C. You have to give to the basis A to get B. So C is 3 over 5. If you go above, you see from the beginning that A is square root of 2. So we need to raise square root of 2 to the power 3 over 5. Okay, so look at the first way. Square root of 2 can be written as 2 to the power 1 over 2. 2 to the power 1 over 2 to the power 3 over 5. So this is a power of power, and the result is the power with the same basis and as exponent the product of the exponent. So 1 over 2 times 3 over 5 is 3 over 10. So this means that we can take a root of order, the root is given by the order of the root is the denominator of the exponent, which is 10. This means also that you can put 2 inside, but you have to raise it to the power 3. So I wrote, I don't know what guys, even what I'm trying to do. So I wrote cubic root, root of order 10 of 8, which can be written as 8 to the power 1 over 10. Okay, I repeat, 1 in this proof can follow the procedure that likes more. But 1 over 10, guys, can be written as a product of 2 powers, 1 over 2 times 1 over 5. Okay, so this term can be written as a power of power, as 8 to the power 1 over 2, everything raised to the power 1 over 5. So saying that this is 1 over 5 means that you can take the root of order 5 of who? Saying that 8 is raised to the power 1 over 2, it means that you can take then the root of order, simply the square root of 8. Say, yes, I did this stupid step only because I wanted to get the result exactly written in this fashion. So we have just shown that really, yes? I don't hear, guys. Then here, guys, more simply, I don't hear you guys. Are you talking? Are you asking me something? I don't hear you. No? Okay, we look at this one because I did it, or simply a to the power c, so square root to the power 3 over 5. This means that you have to take the root of order 5 of square root of 2 to the power 3. Okay, how can you write it as a power of power? I mean, you can rewrite square root of 2 as 2 to the power 1 over 2. So you have 2 to the power 1 over 2 times 3, which is 2 to the power 3 over 2. Again, rewrite it as a power of power. You can write it as 2 to the power 3 times 1 over 2. So 2 to the power 3 raised to the power 1 over 2, which is, so inside this is square root of 2 to the power 3, which is 8, and you get the same result. So I know it's boring, but if you if you know, because these are a lot of things are of things of high school, but if you forget them, if you don't remember them, by doing this exercise, which is, I know if you know the properties are very boring, I understand, but if you know, if you don't remember the properties, it's a useful way because you have a lot of time to apply the rules to, and so you can remember them. So by doing this exercise again, if I mean, only if you have troubles. If you do not have trouble, but for you is everything boring, as I hope, it's, I mean, do nothing at home. But otherwise, it's better if you do the exercise again. Now, point 4, well, nothing. We will not do this exercise. I'll skip this exercise for you. If you want, guys, if you want, at home, only if you want. If you don't want, who cares? Try to. Here there are all the solutions with all the steps, so you can do them if you want. Here I simply simplify the following expression to get logarithm with basis a of b. So you have to show that logarithm of this formula, guys, is equivalent to this one. But here I told you the formula I used and I showed you all the steps. So if you want to do, because these are not properties that you have to remember, okay, something, but to make practice, if you want to make practice, some practice with further practice with the property of logarithm, do this proof, but I repeat that I reported all the steps. So maybe for you are useful to review the properties. We already applied the properties several times with number. Here there are letters, but nothing changes. Okay, guys. No, we still have to work, but at a quarter to 5, I let you go, guys. I imagine you are tired. I'm also tired. I don't know why. Then I have another lecture. So now go back to the function of one real variable, because I told you that we needed, I did this review of powers with real exponents and of logarithms, of the logarithms, because I want to introduce, to review with you, to see with you exponential function and logarithmic function. Sorry, drink a little bit of water. I think I told you that I live in the countryside. Here they have trees of apples, and they work continuously around me. So for this reason, you hear this noise. I hope now they go far, because they closed with all the doors and windows closed. Is not really. It's a little bit hot, so I need to. Okay, stop, guys. Exponential functions. So here is the general definition of an exponential function. Exponential function, guys, as I told you, you write f of x or you write y is the same. F of x equal to a to the power x, where a is, I tell you the meaning, belongs to R0 plus. What do I mean for R0 plus? 0 here and plus here. This means that a is a positive, a strictly positive real number. So this means that is a set of the of the positive real numbers without the 0 and minus the element 1. Remember that when I introduced you, I reviewed with you in the previous file the property of powers. I told you that the basis a was positive and different from 1. This essentially means, no, essentially, this means that a must be strictly positive. So a, when you have an exercise, is a number, a given number, which must be positive, it cannot be 0, and it cannot be 1. Okay? And this was true also in the definition of logarithms. So, the domain of an exponential function is given by all x belonging to R. So the exponential function itself never imposes restriction on the domain. X is defined everywhere, so the domain is x belongs to R. We need to distinguish two cases. A first case, the basis A is bigger than 1, and the case is B, the basis is a number between 0 and 1. So, and here I plotted the graph of the exponential. So this is the graph of the exponential function when a is bigger than 1. What I'm saying, all exponential function with basis a bigger than 1, for example, f of x equal to 3 to the power x, f of x equal to 2 to the power x, f of x equal to square root of 3 to the power x. Whenever the basis is greater than 1, the shape, guys, the shape is this one. Obviously, depending on the basis, you may have that a function increases. For example, you have something like this. I don't print, okay, or something like this, okay, like we did before for other example. But all exponential functions with basis greater than 1 have this type of pattern, okay, this shape. On the okay, now maybe I provide explanation. Let me see. Yes? No? Okay, and other things, but then I explain, okay, then I explain, okay. Now, in the case in which the basis is a number between 0 and 1, and remember, 0 and 1 are not included, all the exponential function like this have this shape, okay, have this shape. For example, 1 over 2 raised to the power x, 1 over 3 raised to the power x, 2 over 5 raised to the power x. In all these cases, the basis is a number between 0 and 1. So in these cases, we have a shape like this. Now we will discuss it, we will see it a little better. Observation. This is true for all type of exponential function. A to the power x is strictly positive for all values of x. The basis is positive, guys. Whenever you give to the basis a real number, what you get is still a positive real number. So what I'm saying is that all exponential functions have graph lying above the horizontal axis. So in both independent, and this occurs independently by the basis. So when you have an exponential function, you can already cancel everything below the horizontal axis, okay? Because the graph will lie always above the horizontal axis. Furthermore, they share, these two kinds of exponential functions share in common another things. That is, both exponential function passes through the point, independently by the basis, through the point 0, 1. You see, 0, 1. Why, guys? Which is f of 0? F of 0, which is the exponential function, a to the power x. So a to the power 0. A to the power 0 is always equal to 1. So you see, independently by the fact that the basis is, for example, 2 or is 1 over 2, 2 to the power 0 is 2, is 1. 1 over 2 to the power 0 is still 1. So another thing they share in common is this one, the fact they all pass to the point 0, 1. So they are both positive and they both pass through the point 0, 1. Okay? Independently by case A or being talking about case B. Now, look instead at this one. You see that when the basis is greater than 1, the exponential function is increasing. In particular, is strictly increasing. Why, guys? Think with me. Consider a numerical example, or maybe I did it later. Okay, now consider with me a numerical example, which is a case of a basis greater than 1. F of x equal to 2 to the power x. Let me write here. F of x, consider this case, f of x equal to 2 to the power x, which is, for example, f of 0, you know, f of 0, when x is equal to 0, f of 0 is 1. Which is f of 1? F of 1 is 2 to the power 1, so is 2. F of 3, to say integer number to me, is 2 to the power 3. So when x is equal to 3, the value of the function is 2 to the power 3. So you have to go above, which is 8. As you can see, as you increase the value of x, the value of y increases faster and faster. Because if you consider, for example, 2 to the power 4 is 16. Okay? Now, what does happen as as you move in this direction? Well, as you move in this direction, as x becomes more and more negative, the value of the function becomes smaller and smaller. For example, which is the value of the function when x is minus 100? You have, guys, f of minus 100 is 2 to the minus 100, which is 2 to the minus 100 is 1 over 2 to the power 100, which is a very small number, almost equal to 0. So in other terms, as you move in this direction, the value of the function decrease, but it's still positive. So you have a pattern like this. If you try to make the same experiment with numbers that we did together, you will see that you have a complete opposite situation when the basis is a number between 0 and 1. Suppose, for example, that your basis is 1 over 2. And suppose that you want to evaluate the value of your function when x is equal to 100. Suppose it's here 100. You have 1 over 2 to the power 100, which is 1 over 2 to the power 100. So 1 divided a super big number, which is essentially approximately equal to 0. So bigger x, smaller the value of the function. So the function decrease, becoming closing and closer and closer. Sorry, not closing, becoming closer and closer. Che do marrons in English, Italianized these noises. Sorry, guys. So becomes closer and closer to the x-axis. Ok? Ma no, ma adesso proprio qui si mettono. On the contrary, guys, what does happen when, for example, x is minus 100? Suppose that x is minus 100. Suppose minus 100 is here. What does happen when x is minus 100? You have, which is the value of the function. Remember, we are in the case 1 over 2 to the power x. So 1 over 2 to the minus 100, we did the property until now. 1 over 2 to the minus 100 can be obtained by easily by change the sign of the exponent and by taking the reciprocal of 2. So I repeat, 1 over 2 to the minus 100 is 2 to the power 100, which is a very huge number. You have to go above. So what I'm saying that when the basis is a number greater than 1, your exponential function is strictly increasing. When your basis is a number between 0 and 1 not included, your function is strictly decreasing. I think I told everything about the exponential function. Yes, I wrote everything here. Okay, the most famous exponential function is the exponential function with basis e. E is called Euler number. Sometimes call it Nepero number, but I prefer to call it Euler number. It's because it's Euler. Maybe someone called Euler also Nepero. So Euler number, which is the graph of the e to the power x. The Euler number is like the pi, is 2.718288, etc. Obviously, guys, e is the basis, is equal to 2 point something, who cares, which is greater than 1. So this is an exponential function of the first kind, that is an exponential function which is strictly increasing because the basis is greater than 1. If you want to plot, suppose you want to plot the graph of the function intuitively of y equal to 2 to the minus x. Well, first of all, how can you rewrite 2 to the minus x? Change the sign of the exponent, but if you change the sign of the exponent, you have to take the reciprocal of the basis. So 1 over 2 to the power x. So which is the basis? 1 over 2. So the basis 1 over 2 is a number between 0 and 1. So we are in case B. So the graph, it's similar to this one. Okay. Now let me see how long is it. I want to finish logarithm and then we stop. We are at page 13. We will not do 13. No, this is material, but we will not do 13. Not today, but also we will not do inverse function. Here is present, but only for people interested, but we will not do it. So let me explain this one. We have last 10 minutes. We work still for 10 minutes because I told you that I let you go at 7. At 7, yes, at 7, at 5 p.m. At a quarter to 5 p.m. Okay. Logarithmic function. In this case, we write f of x or y equal to logarithm with basis a of x. So x is the argument of a logarithmic function. A is the basis. F of x, which is also y, is the logarithm. The exponent you have to give to the basis a to get x. As I told you, a must be positive and different from 1. So, as we did previously. Guys, let me see if I wrote it below. No, I make an observation now. I make an observation. How can you rewrite? Which is the definition of a logarithmic function? So maybe it's good if you write it if you still have the strength to do it. So as I told you, this is the function y equal to logarithm with basis a of x. So this is equivalent to say what? Y is the logarithm. So if the exponent you have to give to the basis, so the basis is a to the power a to the power y equal to x. Okay, guys. So saying y is equal to logarithm with basis a of x is equivalent to say that a to the power y is equal to x. A is the basis, which is positive and different from 1. And as I told you, what kind of function is this one, guys? A to the power y is a power function, which is strictly positive. So this term is strictly positive. Since the first term is equal to the second, also x must be strictly positive. This is the reason why the domain of the logarithm is always the argument bigger than 0. The argument is x in this case, so the domain of the logarithm is x greater than 0. And this comes exactly from this equivalent representation. Or in general, if you remember, alternatively, you remember that the logarithm of a negative number does not exist, but the reason for which it doesn't exist is it comes from the definition, which is this one. A to the power y is strictly positive, is equal to x. And so first hand side is positive, so the second hand side must also be strictly positive. Here I plot, we had to distinguish again two cases, the cases in which the basis is greater than 1 and the case in which the basis is a number between 0 and 1. Remember, in both cases, the argument must be strictly positive, so you can cancel everything for x negative, here, here, here. As before, independently by the basis, the logarithm passes through the point 0, 1. Why, guys? Guys, because suppose that y is equal to 0. Guys, y equal to 0. Which is the exponent you have to, suppose that y is equal to 0, okay? Give 0 as exponent to a, you get a to the power 0, which gives you x, which is equal to 1. But we studied also before that logarithm with basis a of 1 is equal to 0. So when x is equal to 1, y is equal to 0, because this is the property, I do not remember, B, C, D, I think E or F. However, if you don't remember the property, simply say, what does happen when y is equal to 0? Which is the point of intersection of the logarithm with the horizontal axis? You have to put y equal to 0. So apply this definition, a to the power 0 is equal to 1, so x is equal to 1. In fact, you see, as I wrote here, all the logarithm passes through the point 1, 0. 1 abscissa and 0. Furthermore, the other observation I make for the moment is that if the basis a is bigger than 1, the logarithm has this pattern, is a increasing function, strictly increasing function. If the basis is smaller than 1, the logarithm is a decreasing function. Okay. Here I did the sketch of some graph. Well, you never write, guys, y equal to logarithm with basis e of x. The notation used for most spread for logarithm with basis e of x is ln of x. So as the exponential function most famous is y equal to e to the power x, about logarithm, the most famous is the logarithm with basis e, but you never find it written in this way, unless they explain it for the first time, but you find in 90% of the cases, no, we say 80% of the cases, ln of x. In some cases, you read log of x, but this log of x is confusing. So it's better to write ln of x. Why log x is confusing? Because some authors, 20%, use log x to mean logarithm with basis e. But unfortunately, the 80% of the authors use log x to mean logarithm with basis 10. So use y equal to ln of x, which means logarithm with basis e of x. But as I told you, e is the Euler number, which is 2.718, etc., 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 which is greater than 1. So which of the previous two patterns is the one? This one. This is the pattern. If you want to plot very quickly, guys, very quickly, the graph of the logarithm with basis 1/2 of x, you observe that 1/2 is a number between 0 and 1. So we are in the case in which the logarithm is strictly decreasing. So you have something like this. Okay. Now, last examples, and I told you, we arrive here and then we finish. No, ce n'è un altro, no, quest'altro no. Okay, no, we arrive here, guys, okay? Find the domain of y equal to ln of x minus 2. As I told you, guys, the logarithm is well defined if and only if the argument is greater than 0. Which is the argument of this logarithm? X minus 2. So in order to find the domain, you have to set x minus 2 to be greater than 0, from which you get x strictly greater, strictly greater, not greater or equal to 0, strictly greater than 0, so x greater than 2. If you want, you can stop here, or if you want to write it better, you can, by using the notation of interval, you have x belongs to 2, which must not be included, to plus infinity. Look at the second one, y equal to logarithm of x to the power 2 minus 4. Again, the logarithm is defined if and only if the argument is greater than 0. So you have to set x squared minus 4 greater, strictly greater than 0. Guys, please, what is it graphically? Y equal to x squared minus 4 is a parabola. Which is the sign of this parabola? Remember, you have to look at the coefficient a of x squared. Which is the coefficient a? 1. So this parabola is like this, is convex. Okay. Does this parabola have intersection with the horizontal axis? You have to set x squared minus 4 equal to 0, from which you get, guys, minus 2 and 2. So your parabola is something like this. I will not do it perfectly. Here you have the minus 2, here the 2. So you see, it's positive for value smaller than minus 2 and for value bigger than 2. So here I wrote x smaller than minus 2, union x greater than 2. If you want to use the other notation, you have x belongs to the interval from minus infinity to minus 2, which is not included, union from 2 not included to plus infinity. The last one, y equal to logarithm of cubic root of x plus 1. So in order for this logarithm to be well defined, we need to require that the argument of the logarithm must be strictly positive. So cubic root of x plus 1 must be strictly positive. But a cubic root is strictly positive when, if the argument or the radicand is strictly positive. So this is equivalent to say that the radicand is strictly greater than 0, from which you get x greater than -1, and so the domain is x belonging to the interval, open interval from -1 to plus infinite. Okay, guys, we stop here. Tomorrow we continue. We will not do inverse function. No, it's here, but we will not do the inverse function. But this was, I do it in the bachelor, but we avoid, and here we avoid, because we have more important things to do. Maybe, yes, I will show you something about symmetries and shift. Then we go on with other files. I will show an example to make practice with the shift, and okay, we'll do it together. Maybe I will show something about logarithmic equation and exponential. Yes, because there is something, and then we will see what we can do tomorrow. Okay, guys, sorry. Now we finish, and then you can go. I hope that now for everyone the recording will be available on this new room. I hope. And so, guys, what I'm saying, con chi sto parlando? Siete ancora? Are you still here, guys? No, now 8 already died.
Yes, we're here.
Yes.
Okay, guys,
Yeah,
you can go. You can rest. Rest. You have also to okay. Not to study. Go, guys. You have to rest because you need to dovete rinvigorirvi, riprendervi, insomma. You have to recovery, okay? You have to recovery. Drink, eat, be strong, and see you tomorrow for another battle of 6 hours. Okay, guys, if you have question, I answer your question. Oh, I stopped the recording, guys. Remember, for this, we will not have an exam, okay? So instead, for econometrics crash course, we will have a test at the end. We will decide. Okay, I stopped the recording. If you have some question, you can